Continuing on with our conformation analysis, now we're going to look at a little bit of a different structure. Okay, we still have the cyclohexanes that we're working with, but now we're going to work with cis and trans isomers. Okay, remember, cis and trans isomers are what we call geometric isomers, and the only thing that is different between them is whether something is going on the same side. So H is on same side, and here the hydrogens are on opposite side. Okay, so that's how this is. So for example, let's take a compound 1,2-dimethyl cyclohexane, and I'm not going to say what the relationship between the two is, which means that I'm just saying it is a cyclohexane, and on carbons 1 and 2 there is a methyl. But because it's a cyclic compound and you can't rotate the bonds, there has to be a certain relationship between these two, which means either both of them are going at the front or both of them are going to the back. Okay, so for example, here, if they're on the same side, this is a cis relationship, and then if they are going on the opposite directions, then this is a trans relationship, okay, between these two. So let's go ahead and draw the conformers for these two structures. So I'm going to draw for the cis first, and here remember they are on the same side, okay, same direction. That's the important thing. So here we go, parallel lines, parallel line. Now the cis in this case, okay, which means same direction, which means if something is going up, the other one is also going up. It's nothing to do with the axial and equatorial. Okay, so if I draw my methyl group going up, then the other methyl group also has to go up. Okay, that is cis. Now the flip side of that is when I draw the other one here, and now my CH3 that was going up is still up. Remember, this one is going to come down, this one is going to go over here. So now this CH3 is going up, and this CH3 which was equatorial over here, this CH3 is also going to go up. Okay, so these are both cis relationship, okay, to each other. Now in this case you have one axial and one equatorial group. Here also you have one axial and one equatorial. So which means that both of them are same, okay, in energy. There is no difference between the two. So let's go ahead and do the trans now and see if it makes any difference. In the trans, we have CH3 going up. It means that the other CH3 must be going down, and these two happen to be axial. Okay, now for the other side, the flip side. Now the CH3 that was going up is up equatorial. The CH3 that was going down axial is now down equatorial. Okay, so now we have two axials and here we have two equatorials. Okay, so again with the axials we have an issue of these axial hydrogens, and there's that interaction going on, and with this CH3 over here there is that interaction going on. Okay, and so this one is not stable, whereas this one is more stable. So equatorial groups in general, if they are, if you have large groups, they should be in the equatorial position. Okay, that's when you will have more stability. Okay, let's do another one. Let's take trans 1-T-butyl 3-methyl cyclohexane. Okay, all right, so draw the structure out first so we know what we're talking about. It's a trans relationship, so which means you have one T-butyl, and the T-butyl group is the bulky group. Okay, so 4 carbons, remember? There, that's the T-butyl group. And the 3-methyl, 1, 2, 3, and this is trans, which means that here is my CH3 group, okay, over here. Okay, now for the first structure, parallel lines, beautiful lines. And on my 1 carbon, I will have the T-butyl. I will draw it like a T. Okay, so here's my T-butyl group. Since this is trans, one of them should be going up, the other one should be going down. Okay, that's the important thing. So 1, 2, 3. This is my 3rd carbon. So here, this is going up, which means here my methyl group should be going down. Okay, so here this is T-butyl, which is going up, which is my axial hydrogen is going down. Here my axial hydrogen is going up. If this is going up, then my equatorial is going down, and that's where I need to draw my CH3, because the relationship between the T-butyl and the CH3 has to be trans. Okay, and so this is axial and this is equatorial. Okay, and that's how this turns out to be. Again, remember, this up and down has to do with the fact that this is a trans. Okay, the axial and equatorial have nothing to do with it. They just happen to be axial and equatorial. Now for the flip that we will do, and the T-butyl group is going up, and now it will still go up, but now it is going to be equatorial, but still going up. Okay, because that carbon has moved down. And on the 3rd carbon now, which we had the methyl group was going down, so it will still go down, but now this is going to be axial because it was equatorial before. So this is axial. Okay, and this is going down. Okay, now when you look at these two structures, okay, over here, you have to look at the bulky group. So the bulky group is the T-butyl group. So the T-butyl group should be equatorial, okay, and it should be equatorial because that's when you get stability, okay, which means that this structure is going to be more stable because the bulky group, which is the T-butyl group, is equatorial. Okay, so between the methyl group being axial and the T-butyl group being axial, the T-butyl causes a lot more steric hindrance. Okay, that's how you would do conformation analysis for cyclic compounds and if you have two different groups.